Hey y'all. In today's video, we're going to learn how to be able to predict the relative strengths of different acids. In order to do this, we're going to need to lean upon a lot of the things we learned back in drawing Lewis structures and also some of our earlier stuff about Coulomb's law. So let's go ahead and get started. The first thing to remember is that acidity means that the hydrogen on a molecule will pop off as an H+. So to be an acid means that you need to be able to have one of your hydrogens on your molecule fly off as a hydrogen ion. So what makes an acid stronger? Well, the higher likelihood that one of your hydrogens will pop off means that you are a stronger acid. There are three things that can make a hydrogen more likely to pop off. The first is that the bond between the hydrogen and whatever it's attached to in the acid becomes weaker. The second is that the bond between the hydrogen and whatever it's attached to in the molecule becomes more polar. And the third is that the anion that is produced as a result of the hydrogen popping off becomes more stable. So these are the three factors that we can always lean on and rely on as a justification for why an acid is stronger. Now let's take a look at the three different types of acids that we deal with here in chemistry. The first type of acid is known as an oxyacid. And as the name suggests, oxyacids are acids that have oxygens. So oxyacids that we looked at all year long would be like nitric acid and sulfuric acid. Those are acids whose anions have oxygen within them. The second type of acid that we deal with are our binary acids, things like hydrochloric acid and hydrobromic acid. These are acids that have two elements in them, and with the cation of H+ versus the anion of just an elemental ion. The third type of acid that we deal with in chemistry are carboxylic acids. Admittedly, we don't talk about these much here in this course. However, they're really common in biochemistry and organic chemistry because carboxylic acids are organic acids. Again, we're not going to talk about them a lot, but I do want you to understand why they're acids in the first place, and amongst carboxylic acids, what'll make them stronger. So how does bond strength vary within an acid? Well, really within any bond, we can determine its strength based off of two factors. The first factor would be the bond length. So if we look at bond length, it is inverse to the bond's strength. The longer the bond is between the hydrogen and the anion, the stronger that acid will be. So for instance, hydrochloric acid is weaker than hydrobromic acid, and hydrobromic acid is weaker than hydroiodic acid. And it's all because the iodide atom is bigger than the bromine ion, which is bigger than the chloride ion. The way the polarization of the bond between the hydrogen and the anion affects the strength is that the more polarized that bond becomes, the weaker the bond is, and therefore the stronger the acid becomes. So a more polarized bond between the hydrogen and the anion creates a stronger acid. The way polarized bonds impact the binary acids is by the electronegativity of the anion. As the anion becomes more electronegative, the acid becomes stronger. So if we look left to right on the periodic table, what we see is electronegativity increases. So does the strength of the acids. So if I'm going to compare H2S and HCl, HCl is a stronger acid because the Cl- as an ion is more electronegative. That Cl atom is more electronegative than the S atom. As a result, the bond between the sulfur and the hydrogen is less polar. The bond between the chloride and the hydrogen is more polar. The more polar the bond is, the weaker the bond becomes. More polar means less electron density. Less electron density means it's easier to break that bond, and the hydrogen ion would pop off. The way polarized bonds impact oxyacids is through the idea of induction. And so when we have an oxyacid, like for instance, nitric acid, HNO3, the hydrogen is bound directly to the oxygen. As a result, what ends up happening is the other two oxygens are pulling away electron density from that hydrogen bound to the first oxygen. In nitrous acid, the hydrogen is still bound to an oxygen, but you only have one other oxygen that is inducting or pulling electrons away from that bond. As a result, the nitric acid is a strong acid, the nitrous acid is a weak acid. This holds true for all oxyacids. As you increase the number of oxygens of an oxyacid, the acid becomes stronger. Great example, HClO is a weak acid. HClO2 is a weak acid. HClO3, strong acid. HClO4, also a strong acid. So if we look at through the chloric acid family, what we see here is that as we add more and more and more oxygens, the oxyacids become stronger. The reason for that is because the bond becomes more polar and thus weaker. Also in oxyacids, the central atom's electronegativity makes a difference. So let's compare two oxyacids that have the same number of oxygens but a different central atom. So if I compare HSO3, sulfurous acid, and HClO3, which is chloric acid, what we end up seeing is the fact that the HClO3 is a strong acid, whereas HSO3 is not. The difference between the Cl and the S are the electronegativity. Cl is more electronegative. So again, this idea of induction, we're pulling more electrons away from the hydrogen, which is bound to one of the oxygens. It happens to a greater degree in the HClO3 and to a lesser degree in the HSO3. Therefore, HClO3 is a stronger acid. One other way to strengthen an acid would be to inherently stabilize the conjugate base. And one of the most common ways to stabilize a conjugate base is through the process of resonance. Resonance stabilization, which is the delocalization of electrons, where it decentralizes a formal charge. So the formal charge gets spread across the entirety of the molecule or ion, is going to overall stabilize an anion from an acid. The more stable the anion becomes, the stronger the acid becomes. Carboxylic acids are actually acids largely because of the stability of the conjugate base. Carboxylic acids, when they shed their hydrogen, inherently will have resonance because the COOH, one of those oxygens, is double bound. As a result of shedding off the hydrogen ion, the other oxygen will now participate in a resonance stabilization. However, within carboxylic acids, we can also change their strength based off of the same idea of induction. As we attach or substitute more electronegative atoms into a carboxylic acid, so like in this example, where I take the hydrogens of one and I replace them with fluorine atoms, what we see is the acid becomes stronger because the fluorines are going to pull further away electrons from that hydrogen bond. So again, it's a lot of the same basic ideas, whether it's bond length or bond polarity, that impact the bond strength of the acids. Carboxy acids or carboxylic acids such as this will show the same variance in strength. You probably won't see a whole lot of carboxylic acids this year, but you will absolutely see them in future years if you were to ever take biochemistry or organic chemistry. Carboxylic or carboxy acids can be identified pretty easily just by looking for a single group on the molecule. And that group is the COOH group, where carbon is double bound to one oxygen and then is bound to a single bound to another oxygen, which has a hydrogen on it. So again, it's COOH, carbon, double bond one oxygen, single bond another oxygen, which is bound to the hydrogen. That's how we recognize carboxy acids. So that wraps up today's video. Let's do a quick recap. Today we learned how to predict which of two acids would be stronger. In this video, we started by looking at the three real factors that can impact the strength of an acid: the length of the bond, the polarity of the bond, and the stability of the conjugate base. When we looked at length of bond, we were talking mostly about binary acids. Binary acids included HCl and HI. And remember, as we went down the periodic table and the size of the anion got bigger, the acid became stronger because the bond became longer, and the longer bond is a weaker bond. When we looked at the polarity of bonds, this affected both binaries and oxyacids as well as carboxylic acids for various reasons. For the binary acids, as we went left to right on the periodic table and the central atom or the anion became more electronegative, the acid became stronger. With oxyacids, as we added more oxygens, the bond became more polar and therefore this acid became stronger. And for carboxylic acids, as we substituted more electronegative atoms on our molecule, again, we induced a greater movement of electrons away from the bond, and the bond became stronger. The acid became stronger. Finally, we talked about the stability of anions, and we focused mostly on carboxylic acids for this. However, it also applies to the oxyacids to some extent. And when we talk about resonance stabilization, a lot of what creates resonance stabilization is the fact that we have double bonds involved, and those double bonds can delocalize electrons through the process of resonance. This reduces our formal charges closer to zero, thereby stabilizing the anion as a whole. Today's video was written, directed, produced, and edited by Rachel Q. Thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one.